A rock sat in the ground for 4 billion years. It was dull, reddish-brown, heavy, and completely unremarkable. Farmers stepped over it. Children kicked it aside. Builders used it to fill gaps in walls. Nobody looked at it twice because it looked like nothing, like dirt pressed hard, like the earth itself. Buried inside that rock was the material that would one day hold up the tallest buildings ever constructed, carry freight trains across continents, form the hulls of the ships that cross oceans, and get hammered into the machines that pulled our species out of poverty. For most of human history, the rock just sat there. Here is what makes that strange. Iron is not rare. It is the fourth most abundant element in the Earth's crust. More than 5% of everything beneath your feet. Mountains hold it. Rivers carry it. The red clay soil across half the world is red because of it. Gold is rare, and we found gold 7,000 years ago. Tin is rare, and we crossed continents to get tin. Copper is uncommon, and we built an entire age on it. Iron was everywhere. Iron was the last one we learned to use. That is the question. Not how we eventually found iron. Why the most common metal under our feet was the last metal we ever reached. The answer has almost nothing to do with searching. It has everything to do with fire, and specifically, with a fire that was not hot enough. For nearly 2 million years, human technology was stone, flint, obsidian, quartzite, sharp enough to cut meat and skin an animal, but brittle. A stone axe could split wood, and one hard blow against bone shattered it. Break the edge, and the tool was finished, because stone cannot be reshaped once it is made. Then, roughly 7,000 years ago, in the Balkans and Anatolia, someone worked out how to smelt copper. That was already a small miracle. Realizing that certain greenish, blue-tinged rocks, placed in a hot enough fire, would surrender a soft, shining liquid that hardened into whatever shape you chose. Pure copper is soft, though. A copper blade bends rather than cuts when it meets something tough. So metalworkers, they would not have called themselves that, made a second discovery. Mix copper with tin, roughly 9 parts to 1, and you get something harder and tougher than either metal alone. You get bronze. Bronze ran civilization for 2,000 years. The first cities, the first writing, the first empires, all of it built on an alloy that needed 2 ingredients. That was the problem. Copper was reasonably abundant. Tin is not. Tin sits in a handful of specific places on Earth, parts of what is now England, Central Europe, Central Asia, for Egypt, for Mesopotamia, for the palaces of the Aegean. Getting tin meant organizing trade across thousands of miles of land and sea. Ships carried tin ingots from Cornwall down through the Mediterranean. Overland caravans hauled it from Afghan mines toward the cities of the Near East. These supply chains were fragile. One war, one broken agreement, one storm that took a merchant fleet, and an entire civilization could lose the raw material for its most important tool. The element that would have solved this problem forever was sitting in the soil under every one of their feet. They had no way of knowing it. The reason is chemistry, and it is almost unfair. Iron has an extremely strong attraction to oxygen. Gold appears in nature as shining nuggets in riverbeds. Copper sometimes turns up as raw reddish metallic chunks. Iron, given any exposure to air and water over geological time, converts to iron oxide, rust. Almost every trace of metallic iron that ever existed on the Earth's surface has long since been turned into dull reddish stone. Almost. There are freak exceptions. On Disco Island, off the coast of Greenland, native iron survives inside basalt, and Inuit communities were cutting tools from it long before any European arrived. But those places are geological accidents, and there are only a handful of them on the planet. Everywhere else, what ancient people saw when they looked at iron ore was red rock. Brown rock. Heavy rock. Rock that looked exactly like rock. Because as far as any evidence available to them could show, it was rock. There was one other exception, and it came from the sky. Nickel-iron meteorites are fragments of the metallic cores of asteroids that broke apart in the early solar system. When one survives the fall through the atmosphere, it brings something that does not naturally exist here: native metallic iron, already pure, already usable. These objects are unmistakable in the hand, far denser than ordinary stone, magnetic. Strike one with a rock hammer, and it does not chip or shatter, it dents. Cut it and it gleams. Everything about a meteorite is wrong for a rock, and the people who found them knew immediately they were holding something unlike anything else on Earth. They were right. In Egypt, iron was given a hieroglyphic name translating directly as metal from heaven. That was not poetry. Egyptian scribes were describing the only iron they had ever seen. Sumerian texts used a sign combining sky and outside. Hittite documents called it the black iron of the sky. The oldest iron objects we have predate the Iron Age by 2,000 years, and none came out of the ground. At Gerzeh, a pre-dynastic Egyptian cemetery, archaeologists recovered 9 tube-shaped beads from around 3200 BC. The nickel concentrations are unmistakably meteoritic. Tutankhamun was buried with a dagger whose blade runs to nearly 11% nickel. Tablets from the Assyrian trading colony at Kanesh record a metal, generally read as iron, priced at up to 40 times silver by weight. Kings gave it to other kings. It was rarer than gold, and it fell out of the sky. Now the thermodynamics, because this is where the story actually turns. Copper melts at 1085 degrees Celsius. Bronze melts lower, around 950, because alloying with tin drops the melting point. Bronze Age kilns were built to hit exactly this range. A good pottery kiln ran between 1000 and 1150 degrees, enough to turn copper and bronze to liquid and pour them into molds. Pure iron melts at 1538 degrees. That gap, roughly 400 degrees between what an ancient furnace could reach and what iron demanded, is not an engineering inconvenience. It is a different category of problem. Here is the part that should bother you. They tried. There is archaeological evidence that early metalworkers put iron-bearing rocks into copper furnaces and waited for liquid metal to pool at the bottom. Nothing came. The iron did not melt. It did not flow. It sat there, red-hot, stubbornly solid, offering nothing at all. Every reasonable inference from every piece of evidence they had said the same thing. This rock is useless. For 1,000 years, furnaces across the ancient world were already doing the thing that would unlock iron. Nobody opened the right one. What happened next was not a search. It was a slow accumulation of furnace knowledge across generations of people who had no idea they were building toward anything. The first improvement was charcoal, wood heated slowly in near total absence of oxygen until what remains is almost pure carbon. It burns hotter than timber, steadier, cleaner, and inside a furnace it lifts the thermal ceiling substantially. The second was enclosure. Early fires were open hearths. Then someone built walls of fired clay and fieldstone, tall enough that a column of rising hot gas pulled fresh air in through the bottom. The taller the shaft, the stronger the draft, and the hotter the charcoal ran. Nobody designed this on purpose. Builders who made their furnaces taller simply noticed the fire burned better, and kept doing it. The third, and the most important, was the bellows. Leather bags pumping air straight into the base of the shaft through clay nozzles. Forced air does what natural draft cannot. Sustained bellows work could push a shaft furnace to 1200 degrees or more. None of it was done with iron in mind. Bronze smelters wanted hotter furnaces to smelt copper more efficiently and waste less fuel. They were solving the problem in front of them. What they built, across centuries, was a machine capable of something its builders never intended. The likeliest reconstruction, based on the archaeology and on modern experimental metallurgy, goes like this. A copper smelter running a charcoal shaft furnace with bellows put iron-bearing rock into it, perhaps deliberately, since iron-rich rock was sometimes added as a flux to pull impurities out of copper ore, or perhaps because the furnace lining itself was iron-rich clay. Either way, iron oxide ended up inside a shaft, burning between 1,000 and 1,200 degrees. At that temperature, iron ore does not melt. Something else happens instead. Charcoal burning in a partially enclosed space does not combust completely. With limited oxygen, the carbon produces carbon monoxide rather than carbon dioxide, and carbon monoxide is chemically aggressive toward anything holding oxygen. As it rises through the shaft, it meets the iron oxide and strips the oxygen atoms off the iron atoms, one by one. It does not melt the ore. It reduces it. In the solid state, without ever becoming liquid, an oxide turns into metal. What forms is not a shining pool at the bottom of the furnace. It is a dark, porous, spongy lump of iron particles fused together, riddled with glassy slag, still roughly the shape of the rock it used to be. It is called a bloom. Someone broke open the base of that furnace expecting slag and disappointment, and found an object nobody had seen before. Dark, porous. Almost nothing about it looked like metal. Then they hit it with a hammer while it was still hot, and it did not chip and it did not shatter. It deformed. It did not melt. That was the entire point. Here is the inconvenient part of the story, and most retellings skip it. The metal that came out of those first furnaces was not better than bronze. It was worse. A raw bloom is unusable. Iron shot through with solidified slag, porous as a sponge, structurally incoherent. Left alone, it would crack apart. Turning it into something you could hold took hours of the hardest work in the ancient economy. The bloom hauled onto a stone anvil at near-white heat, above 1,000 degrees, and beaten. Every blow squeezed slag out through the surface, collapsed the internal voids, and pressed iron particles into contact until they fused at the atomic level, welding without melting. What you get at the end is wrought iron. Tough, yes. Bendable without fracturing, yes. Also soft. Put a wrought iron edge against bone, or hardwood, or another blade, and it deforms. Measured on a hardness scale, early wrought iron sits well below a properly work-hardened bronze sword. So the question that runs through the next 1,000 years of this story is not why iron was discovered. It is why anyone kept using it. What is remarkable about the people who ran these furnaces is not that they succeeded, it is how precisely they learned to succeed while understanding none of it. They picked ore by hand and by weight. Dense, dark rock from particular formations gave better blooms than light, reddish, earthy material, a rule built entirely out of accumulated failure. They read the flame. An experienced smelter could judge what was happening deep inside a sealed clay shaft by the color of the fire at the top of it. Bright yellow-white meant the reduction was running properly. Dull red meant the charge was starving and the run was already lost. They listened to the bellows. There was a rhythm that corresponded to a productive furnace and a rhythm that did not, and it was taught by ear. They watched the slag. When it drained out of the tap hole, its thickness told them whether the chemistry inside was right, too runny, too stiff, and something needed changing within the hour. The ratio of charcoal to ore, the height of the charge, when to stop. All of it learned by watching, remembered in the body, handed down through apprenticeship. No written metallurgy, no formulas. Observation, memory, and the oral tradition of a workshop. These people had mapped the inputs and outputs of a chemical reaction with real precision, and could not have told you a single thing about why it worked. which is why, across cultures with no contact between them, the blacksmith became something close to a sorcerer. Think about what the work looked like from outside. A man takes dull reddish stones and puts them into a fire. He works the fire with leather bags for hours. He breaks open the base and pulls out a shapeless, spongy mass, heats it again, hammers it until his arms give out. What he hands you at the end is a blade, or a plough tip, harder and sharper than anything that existed before. Nothing visible in the rocks prepared you for the metal. The whole transformation happened inside a fire, where you could not see it. In Greek and Roman tradition, Hephaestus and Vulcan forged the weapons of the gods, figures of awe and unease both, holding power so great the myths had to lame them or exile them to islands. In Yoruba tradition, Ogun is the deity of iron and of war, patron of blacksmiths and hunters. Celtic myth gave the smith god Goibniu weapons that never missed. In Norse stories, the dwarf smiths who forged for the Aesir were the most technically skilled beings alive. 4 traditions, no contact, 1 conclusion. A person who could turn rock into metal held a category of knowledge that sat outside ordinary understanding. The blacksmith shop was the closest thing to alchemy the ancient world ever actually delivered. The thing that finally made iron better than bronze was carbon, and no blacksmith on Earth knew it existed. What they knew was a pattern. Iron left in contact with burning charcoal for a long time came out different, harder, stiffer. A blade that sat in a hot hearth for hours behaved differently from one worked quickly and pulled out. The mechanism took another 2,500 years to describe. Heat iron passed roughly 900 degrees, and its crystal structure changes into a form called austenite, in which the gaps between iron atoms happen to be exactly the right size to hold carbon atoms. Surrounded by burning charcoal, the metal absorbs carbon straight through its surface into those gaps. Less than 1% by weight transforms it. With enough carbon in it, iron becomes steel, and steel can be hardened. Heat it correctly, plunge it into cold water, and the carbon-loaded iron locks into a structure called martensite, which is extraordinarily hard. Hard enough to scratch bronze without effort. The smiths who first made this had not planned it. They noticed it, then built practices around it. Longer soaks, particular quenching routines, specific ways of packing metal against fuel, that reliably produced the harder material. They knew exactly how. They had no framework for why. For centuries after ironworking appeared in Anatolia and the Levant, roughly between 1500 and 1200 BC, it stayed a secondary technology. Bronze kept the infrastructure, the skilled workers, the trade routes, and the prestige. Then, around 1200 BC, the eastern Mediterranean fell apart. Inside roughly 50 years, the Mycenaean palaces disintegrated. The Hittite Empire ceased to exist. Coastal cities from the Levant to Cyprus burned, and Egyptian records describe waves of invaders they called the Sea Peoples. The palace economy that had sustained those long tin routes stopped functioning. Be careful here, because this is where the popular version overreaches. What is not in dispute, long-distance trade broke down, and ironworking expanded sharply afterwards. What is reasonably well supported, bronze became harder and costlier to make in the areas hit worst. What is genuinely still argued over, whether tin specifically ran out and caused the switch, or whether iron was already spreading on its own, and the collapse simply removed the reason to keep resisting it. The honest version is smaller than the dramatic one, and more interesting. A civilization with a working tin supply had every reason to stay with bronze. A civilization without one had a furnace, a forest, and rocks in the ground. Iron did not win because it was better. Iron won because it was the only thing left. And then, over the following centuries, it became better. The consequence was not that iron tools were superior, it was that iron tools were available. Bronze needed copper and tin, and tin needed continents. That made it expensive enough that metal weapons, armor, and farm tools stayed largely with elite soldiers and wealthy landowners. You could not equip a mass army with bronze. Most of a society's working population never owned a metal tool in their lives. Iron ore is nearly everywhere, and charcoal can be made from any forest. A village with a bloomery and a smith produced its own metal and imported nothing. Picture what that meant. A farmer working heavy ground with a wooden ard, scratching a shallow line through soil his grandfather also failed to break, walks to the smith at the edge of the village and comes back with an iron share fitted to the same wooden frame. It bites. The soil turns over instead of parting. Ground that had defeated 3 generations opens in an afternoon. Multiply that by every village in a region and you get more food, from land that had never grown any. The metalworking knowledge that had lived inside palace workshops moved out into ordinary communities, and stayed there. Iron did not spread outward from a single origin either. Several civilizations built ironworking traditions largely independently, and they did not converge. In China, furnace technology went somewhere the Near East did not. By around the 6th century BC, Chinese furnaces could melt iron completely. Fully molten iron absorbs far more carbon, 2 to 4% by weight, producing cast iron, which melts at a much lower 1150 degrees and pours into molds. Brittle, but hard, and superb for agricultural castings. By 31 AD, an official named Du Shi was driving furnace bellows with water wheels, a mechanization Europe would not match for more than 1,000 years. In India, smiths sealed wrought iron with organic carbon inside clay crucibles and held them hot for long periods, producing high-carbon ingots that forged into blades with distinctive banded patterns. Traded across the Indian Ocean, they reached Europe as Damascus steel. The usual story is a guarded secret. The better explanation is less romantic. The specific ore deposits, carrying the trace elements that made the pattern possible, ran out. In sub-Saharan Africa, independent bloomery traditions developed before the Common Era. Some African smelters built tall, natural draft furnaces that preheated incoming air before it reached the charcoal, a thermodynamic principle European engineering would not formally articulate for centuries. If you are finding this as fascinating as we do, subscribing genuinely helps us keep going deeper into stories like this one. 2 myths survive in popular accounts, and the archaeology is fairly clear about both. The first is the Hittite monopoly, the idea that the Hittites discovered iron smelting, guarded it, and released it only when their empire fell. Smelting sites and iron artifacts appear at comparable dates across Anatolia, the Levant, Mesopotamia, and the Caucasus, with no sign of a centralized secret. The Hittites used iron, they did not own it. That myth says more about how 20th century historians expected technology to work, radiating outward from one clever source, than about how it actually develops. The second is the brilliant inventor. Nobody discovered iron and no culture holds the patent. It came out of thousands of small observations by people who had no idea their observations would accumulate into anything. The bloomery had a ceiling. Small blooms, discontinuous runs, brutal labor. Scaling it up meant more furnaces and more people, not a better process. The blast furnace broke that ceiling, a continuously running version of the same idea, tall enough and hot enough to fully melt the iron and tap it from the base. China got there by the early Common Era, Europe through the 13th and 14th centuries. Its pig iron carried too much carbon to use directly, and the problem of burning that carbon back out was not solved at scale until Henry Bessemer's converter in 1856. Cold air blasted through molten iron, tons of structural steel in minutes, no extra fuel. That is the moment the skyscraper became possible. Here is the part worth holding on to. The reaction inside a blast furnace in Pittsburgh or Wuhan today is the same reaction that ran inside a clay shaft on an Anatolian hillside 3,000 years ago. Carbon monoxide stripping oxygen from iron oxide in a hot enclosed space, different by a factor of millions in scale, identical in chemistry. We know it works without understanding, because archaeologists have proved it. Researchers build replica bloomeries from ancient measurements, fill them with charcoal and local ore, pump hand bellows for hours, break open the base, and get metallic iron, every time using nothing the ancient world did not already have. So, why was the most common metal under our feet the last one we reached? Not because it was hidden, and not because nobody looked. Because unlocking it required a furnace that could not do the obvious thing. Melting is the intuitive answer, and melting was permanently out of reach. The path ran instead through a reaction that only happens. Below. The melting point, in a fire hot enough to strip oxygen and not hot enough to liquefy anything. The discovery required a furnace that failed at what it was built for. The limit was not the obstacle. The limit was the condition. Stand in a modern city and look up. The frame of the building above you is steel. The beams under your feet are steel. The rebar inside the foundation, the bridge you crossed, the train that carried you, the ship that brought the goods in the shops around you, the cars, the cranes, the pipes, the cables. Every gram of it was once dull reddish rock pulled out of the ground. Every gram went through a furnace where carbon monoxide took the oxygen off iron oxide and left metal behind. The person who first pulled a lump out of a hearth and found that hammering it made metal was not standing at the beginning of a separate story. They were standing at the beginning of this one,